Welcome everyone to the Aerospace Engineering seminar of today, the 3rd of December. Today we have speaker Georgios Rigas. He started his academic career at Imperial College in London. He actually got his PhD there in 2015. Then after that, he became a postdoc for a bit over a year at the University of Cambridge. And then you moved to Pasadena, California, to get some sunshine for about 3.5 years. You were at Caltech, I think in the group of Tim Colonius. And then in 2019, September 2019, you started your position at Imperial College as a lecturer, and you're giving the talk currently based on work, to my understanding, of that was done at Imperial College a little while ago, and also in very recent experiments. So we look forward to your talk, which is going to be on large-scale coherent structures in turbulent wakes, and the digital floor is yours.
Perfect. Good afternoon, everyone. It's nice to see familiar faces that most of you, I know your names. And Rutin, thank you so much for the invitation. And Nankoa, I hope to see you in person at some point soon. So as you said, today I will be talking about a topic that I really like because it was one of the first topics I started doing research on. It was the turbulent wakes at Imperial College, and I revisited since I started this topic recently. So to start, the motivation was large-scale coherent structures in turbulent wakes, and specifically the automotive industry. So I'm showing this simulation here to emphasize about the complexity of the flow around the vehicle, but also to emphasize about the fact that most of the drag is produced in the near wake of this vehicle at highway speeds. So we spend more or less half of the fuel to move this object, this vehicle, in order to overcome the aerodynamic losses due to the pressure drag in the near wake. And because this drag arises because the pressure difference between the front and the back, any attempt to increase the efficiency, the aerodynamic efficiency, should be done by altering actually the properties in the near wake. So the low pressure region, we're trying to push high the pressure and equilibrate this pressure difference. So there are different approaches. The first one is passive approaches. We improve the aerodynamic design. We can see this can improve a lot also the electric range anxiety in the electric vehicles by changing the drag coefficient. Tesla was able to increase by 50 miles the range of their cars. In California, when I was there, I used to see these vehicles. We don't see them in Europe because we don't have these regulations yet, but they might come soon, which actually by law you're enforced to have aerodynamic devices in vehicles that they can achieve 4 or 5% reduction in fuel consumption. And why these are the only devices that we can see in these tracks, the reason is really simple. Is because we cannot understand the turbulent dynamics of the wakes. And this is really well summarized in this sentence from the recent review of Choi, that there is no real use of base pressure drag reduction devices due to the lack of understanding of the flow in the wake. So we cannot really have realistic base drag reduction devices. So one of the approaches we attempted back when I was a PhD with another PhD student working there, Anthony Oxlade, was instead of using surfaces to actively to passively streamline the body, why we don't use active control? So use a set of jets in the rear of the car so that they pulsate with a high frequency, high amplitude, and create virtually a streamlined body by manipulating the flow in the rear wake. So we went in the tunnel, we designed this axisymmetric bluff body. It took us a while, to be honest, because in the rear base of this body, actually, there is a speaker that is creating a jet that is interacting with the near wake through a small slit around the circumference of the body. And we have base pressure sensors on the base to measure the difference in pressure. So the Reynolds number is 200,000 based on the diameter, fully turbulent regime. And we drive the speaker at different amplitudes or jet momentum coefficients and different frequencies. And on the right-hand side, I'm plotting a map of the drag reduction, or equivalently, the pressure change that we can achieve by driving at different frequencies and amplitudes the jet. So we can see that we can achieve approximately 35% drag reduction, which corresponds approximately to 15 to 20%. This 35% pressure increase, which is 25 to 20 approximately percent drag reduction. Okay, this sounds great as a technique to achieve that. But when we measure the power actually required to drive these jets, we found that the efficiency was approximately 1, so more or less what we spent to drive the actuator was consumed to reduce the drag of the body. So it raises the question, is that a realistic approach to, or a practical approach to reduce the drag? So then we took a break, we went back at the office and we started thinking a bit more about the dynamics of the wake. And what I'm going to be showing you today is what is our current understanding of the flow structures, which will motivate actually some experiments we did at high Reynolds numbers, and also some more sophisticated control that we applied a few years ago and we revisited nowadays with more modern techniques like reinforcement learning. So the first thing we did is we ran a series of direct numerical simulations that was at the CTR summer program a few years ago with Luca Magri and Luca Escalopes to understand the near wake dynamics during the transitional regimes. So we started increasing slowly the Reynolds number, and we saw a sequence of symmetry breaking bifurcations happening. The first one being a spatial symmetry break, so the wake, instead of being rotationally symmetric, is shifted towards one side. And if we plot the vorticity in a plane near the base, we can see actually that the wake has shifted off center, and there is a force, lateral force, such that the center of pressure, for example, in that case, would be off the center of the body. If we keep increasing the Reynolds number, we see a second bifurcation. So we lose now temporal symmetry. Instead of time being a continuous direction, it becomes a periodic direction. In that case, we have the typical vortex setting. So we have a peak in the near wake at a Struhal number of approximately 0.12. And after that, if we keep increasing the Reynolds number, the flow becomes quasi-periodic and fully chaotic. And at high Reynolds number, it becomes fully turbulent. So these regimes, actually to understand them, we performed a linear stability analysis, starting from an operator-driven approach. In that case, we have the Navier-Stokes equations. We linearize them around a base flow. We find this base flow by solving the steady Navier-Stokes equations. So I want to emphasize that these ones are nonlinear equations that we use a Newton method to find equilibria known as fixed points or base flows. Once we have such an equilibrium, we can solve an eigenvalue problem for this base flow to see if there are unstable eigenvalues associated with the symmetry breaking phenomena. And what I want to emphasize is that because the flow is three-dimensional, at some point we have to solve fully a three-dimensional stability problem. So we discretize in all three directions and we find eigenvalues of this large scale system. So starting at low Reynolds number, we have a fully axisymmetric flow. This is the base flow that we examine its stability. So at some point, if we plot the spectrum, we see an eigenvalue crossing the imaginary axis. It has a zero frequency. This corresponds to a steady eigenmode that we can see here, which is associated with a pitchfork bifurcation that breaks the rotational symmetry that we showed as well in the DNS calculations. What happens is that now this is just the linear mode. It tells me the eigen direction of the growth of this instability, but the final saturated regime, which is steady and non-symmetric, can be found by just taking this eigenmode, the unstable eigen direction, throwing it back in the solution, iterating with the Newton-Raphson method, and we end up with a new three-dimensional asymmetric solution, as you can see here. So this is a typical spontaneous symmetry break phenomena that originally all the solutions were symmetric, but because of the symmetry break, actually, what happened is the original axisymmetric flow, which corresponds to this state up here, became asymmetric. It breaks the rotational symmetry. And this actually azimuthal direction in that potential well can be chosen arbitrarily based on the initial conditions for the stability analysis, somehow we have to fix this angle, otherwise it causes degeneracy. So now the fully stable state is the one we see here, and we can continue the stability analysis. So now we have to examine the stability of this fully three-dimensional steady flow, and we find another steady bifurcation at approximately Reynolds number 605. So in that case, you can see that the vortex shedding mode that we plot on the right-hand side is asymmetric, and it has inherited the symmetry properties of the original asymmetric base flow. Again, this one is a linear eigen mode. It doesn't tell us anything about the saturated state, and this is where weak nonlinear analysis comes in. I'm not going to go into details about that, but what I want to emphasize is that instead of stopping at first order, which would be the linear order, if we continue at higher orders, we can get some expressions which are known as Stewart-Landau equations describing the amplitude evolution of the most unstable mode during the saturated regime. And I want to emphasize that these are exact solutions at the order of truncation, meaning that if I throw them back in the Navier-Stokes equations, they're going to give me a zero residual given the accuracy of the truncation. And many other groups, they have extended these techniques actually to fully three-dimensional wakes like spheres. Okay, this summarizes more or less the dynamics at the laminar regime. Unfortunately, the tools are not so evolved to take the same tools and apply them in the turbulent case. So what actually we did is we went to the wind tunnel and we performed a series of experiments to understand what are the dominant dynamics. And what I'm going to try to persuade you today is that exactly the same transitional dynamics that we see in the laminar regimes, they can be observed also at high Reynolds numbers. So one of my PhD students with Jonathan Morrison, co-supervised, he did recently a follow-up experiment of the original experiment we had performed. So he's doing now also time-resolved two-component velocity measurements in the near wake. We can see here a visualization of this flow field. The flow, as I said, is fully turbulent, Reynolds number approximately 200,000, and the separated boundary layer before the trailing edge is fully turbulent. We can see a wide logarithmic region developing before separation. And this is the pressure measurements. We can get pressure measurements as we did originally a few years ago in the near wake, in the base pressure, using 64 pressure traps. So I will just summarize or remind you for some of you that you might have seen these results before, like we started with a base pressure analysis and we performed an azimuthal decomposition because we have the 64 azimuthally distributed pressure sensors. We plot the power spectral density of each azimuthal mode, and we plot them in a pre-multiplied spectrum, such that the area we see here corresponds actually to energy. This is really convenient to understand where coherent structures happen, but sometimes it might be misleading because some peaks that we see, actually, they're not periodic solutions, but they're just regions of high energy. So the peaks we identify, the first one is the typical vortex shedding peak at Struhal point 2 with azimuthal wave number m equal ±1. This is straightforward. And we see another peak happening at approximately Struhal point 1 associated with an axisymmetric pulsation of the whole wake, the bubble pumping mode. And back in 2015, we saw also this strange peak at approximately 100 times lower frequency than the frequency of the vortex shedding mode. And actually, to be honest with you, the first time we saw that peak, we said, okay, there is something wrong with the experiment. So we had to change 3 or 4 wind tunnels, revise the experimental setup, try different perturbations, until actually we realized that there is something associated dynamically with this peak. Also here I'm showing the proper orthogonal modes. They don't tell us anything specific with that peak. It just tells us that actually the m equal ±1 is the most energetic one, and the m equal 0 associated with the axisymmetric bubble pumping is the third most energetic mode. So to understand where this peak is coming from, actually, and inspired by the stability analysis results, we defined the center of pressure to give us an order parameter of the symmetry break in the near wake. And actually, this has some nice symmetries. If the flow is rotationally symmetric, the center of pressure will have a 0 value. So that means that the force, the total force on the body is at the center. Whereas if it is non-zero, the value, it will be off center. So we have a symmetry break. And we plot the PDF of that in the 2-dimensional base of the body. So we're quite surprised to see that actually most of the time we achieve a non-zero non-zero center of pressure, which means that most of the time the wake has a broken symmetry. And we said, okay, probably we're going somewhere here. These dynamics, they might be the ones related to the ones observed in the laminar regimes related to the symmetry broken mode. So to show that, what we did, we took all the snapshots of the pressure measurements and we rotated them based on the azimuthal angle of the center of pressure. So we performed a conditional averaging based on the center of pressure, the azimuthal angle of the center of pressure. So on the top, we see the average pressure field, which is axisymmetric. As expected, fully developed turbulence recovers all the broken symmetries. But on the bottom side, we see actually we recover the steady symmetry break that was found in laminar regimes, but now exactly the same mode was found at high Reynolds numbers, and we see it shares these properties, the reflectional symmetry property of the symmetry broken structure that we expected to find. What happens is that this structure at high Reynolds numbers, it doesn't stay at a specific angle, it randomly reorientates, and due to ergodicity, we recover actually at the long time average the full axisymmetry in the near wake. Why would you care about that? Because actually symmetry break is associated with drag, okay? And there is a direct relationship between the center of pressure and the pressure coefficient, or equivalently the drag in of the total drag of the body. So with the brown, I'm showing the radial PDF of the center of pressure. So the most probable symmetry broken direction is this one. And if we conditionally average now the base pressure or the drag, or which is the measure of the drag in the body, we see that we have actually a high drag or equivalently low pressure coefficient. And any attempt to increase the base pressure would imply probably a symmetrization technique. So we would like to achieve a 0 center of pressure in order to increase the base pressure and reduce the drag. These observations as well motivated the modeling approach, because to perform control, we need a model as well. And the inspiration for that came from actually one of the very, very characteristic visualizations that Brown and Roscoe had produced. And this is the mixing layer that we can see in a transitional mixing layer, actually an instability developing and persisting all the way at fully turbulent regimes. And the only difference in that is actually there is some diffusion and some stochasticity introduced in that case. So we can think of the coherent structure actually now, which corresponds to the symmetry broken state, something like a large scale structure that is swimming in a bath of fluid. And if we think about that in this way, actually this is the definition of a Brownian motion. And what we decided to do is we take all the models that we had for the transitional regimes and add some Brownian motion and see how far we can go with that. How do these models look like? They share the same properties as we said from the ones from the laminar regimes. These are the weak nonlinear models, and we add white Gaussian noise. So this is a Langevin equation. This is a stochastic differential equation now that is perturbed by sigma xi, which represents in a phenomenological way the influence of the stochastic turbulence produced either by the wake itself or by the incoming free stream. So this is a stochastic differential equation which is a bit difficult to deal with, but its probability density function actually, which is defined by the Fokker-Planck equation, has a deterministic evolution, and this is associated with a potential and probability. So the potential associated with this flow is shown on the top left, and this model as well. So in the turbulent regime of course, the flow will never be steady, so it will be unsteady and unstable. So a ball, if we think at the center of the potential, would fall down, and because of the random turbulence and ergodicity now, it would reorientate randomly, both in the azimuthal and the radial directions, till we achieve a probability density function that is the one that we have on the right-hand side. How well does the predictions compare with the model? They compare quite well quantitatively and qualitatively. So here we see a comparison of the PDFs. And someone might argue that, of course, turbulence is not Brownian motion or just white Gaussian noise, but actually from a large-scale perspective of view, and if we compare the angular mean square displacement and the radial one with the predictions of the Brownian motion, which tells us that the MSD should scale linearly with time, we see a perfect agreement between the experiment and the predictions of the model, and we can actually recover this diffusive motion that scales linearly with time at large scales. Of course, in the radial direction, due to the curvature of the potential well, we cannot explore all the time scales, like in the azimuthal direction, and actually the mean square displacement saturates, which is also perfectly predicted by these models. And these models, they were only for rotational symmetry, but they can be extended for any kind of symmetry if you have in the experiment, like D4 or D3. For example, a car would have a D4 or D2 symmetry. And now, instead of multi-stability or a continuous symmetry group and a continuous solution, we can have discrete solutions or discrete equilibria that are equally explored, as I said, again, due to ergodicity in our system. Okay, so these normal forms, they can be derived, that they describe the deterministic part, either based on first arguments, based on symmetries. However, in many cases, we might not know actually what is the form, the functional form of this equation, and this can remain unknown. And this is where also modern data-driven techniques can come in. So earlier this year, actually, we published this paper with Steve Brandon and his group, so how to identify stochastic differential equations, but with another difference as well. We can have arbitrarily defined noise that we can also discover, and this noise doesn't have to be white Gaussian. It can be any kind of colored noise, but also it can have also a state dependence function. So we did that for the experimental results of the bluff body, and quite interestingly, we recovered exactly the functional form for the deterministic part that we expected. But for the noise part, actually, we saw that we can achieve an improvement if you have state-dependent noise. And this, we think, is something interesting that might worth further studies in the future. Just very briefly, how we would derive these functional forms. Actually, we use a Cindy type of sparsification. So we have a dictionary, all the possible polynomials that can describe this normal form. And based on a sparsifying procedure, both for the stochastic part and the deterministic part, we can choose the number of modes such that the prediction of the model matches the prediction of the data in the best possible way. And this is all the story about the pressure data. And now I'm going to move to the velocity data and the results from the near-wake experiments. So these are the POD. We can see that the first few POD modes are very coherent in contrast to the completely random wake that we have instantaneously. And to understand a bit more the dynamics of these most energetic coherent structures, we plot again the power spectral density of the amplitude coefficients associated with these modes that we can see here. So the first mode, the most energetic velocity mode, actually has a low frequency component that is approaching Struhal 0. And actually this mode is visualized here, and it compares very well with the one that we found from stability analysis at the low Reynolds numbers. And the mode on the left is the one identified at Reynolds number 600. The one on the right is the one at 200,000 from the PIV measurements. We see two more modes at the Struhal number, 0.2, which is a traveling mode giving rise to the Karman wake. And also we see the axisymmetric bubble pumping mode, which is a symmetric mode, as we can see here, in a frequency approximately 0.1 and a bit lower. However, actually, there is a caveat here. It's like the structures we found, the nonlinear structures, are non-symmetric, meaning that only the linear ones are symmetric. And this raises the questions, do the POD modes we found actually represent the true physics of the system, since they are symmetric, but the underlying dynamics are asymmetric? And of course, the answer is no. And to do that, actually, we performed a conditional POD analysis of the velocity data now. So in the same way, we conditioned the pressure data based on the angle of the center of pressure. We conditioned the velocity data, the state of the wake, based on the amplitude coefficient of the first POD mode, which defines in a way the symmetry break state. So some of the times when this amplitude coefficient is positive, the wake will be at the top side, so it will be reflected towards one side. The rest of the time, it will be on the other side. And if we do a conditional averaging based on this kind of procedure, actually we can recover the two truly asymmetric states that actually can be observed in the nonlinear solutions of the Navier-Stokes equations. We can do that also for the POD modes specifically, and here I'm going to show you the conditionally averaged now POD modes based on the symmetry properties of the wake, and the first one corresponding to the azimuthal symmetry break is now asymmetric. It's not very evident, but I can tell you that the blue is not the same as the red, and this gives rise to this tilted wake towards the one side. The vortex heading mode is more pronounced now with the conditional averaging, that is one-sided because the wake has been conditionally averaged to be only in one side. So we can see also the vortex heading inherits the same symmetries. And it compares very well now with the true as well mode that we found from the stability analysis. We can give also another interpretation of the bubble pumping mode, and actually, although the low frequency mode that we found here is the low frequency reorientation in the azimuthal direction, we have another diffusive time scale which corresponds to the oscillations in the radial direction of the center of pressure or the wake due to the broken symmetry dynamics. So we can think of the bubble pumping mode corresponding to a radial meandering of the whole wake due to the symmetries and that are broken, and we stochastically explore both in the azimuthal and in the radial direction. So that summarizes our understanding, the most recent understanding we have about the turbulent wakes using both the pressure and the velocity measurements. The most important part is the persistence of laminar symmetry break instabilities to fully turbulent regimes. And the last part, the symmetry-conditioned POD, will motivate the next part of my talk, which actually one of my other students, Simon, actually came with a sophisticated way to include any kind of symmetry and create what is called the symmetry-aware proper orthogonal decomposition analysis. So the symmetry we had before was only a rotational symmetry, but there are systems that we can have many other types of symmetries, continuous and discrete symmetries, and these are causing serious problems for modal decomposition methods. So we're gonna use POD that actually we can implement with autoencoders. We use an encoder-decoder type of architecture that we can prove that if we use a linear neural network with just one layer, this is exactly equivalent to performing POD. However, now we can go also to the nonlinear regime, and we can do more sophisticated or more compressed analysis of the flow by replacing the linear neural networks with nonlinear ones. However, in that case, we lose some kind of interpretation of the modes because we don't have specific modes associated with these structures. So I'm going to define what we call an invariant solution, and this is actually what gives troubles to the POD. And specifically, we have a set of partial differential equations, like on the left-hand side in compact form, and that are equivariant, actually under a symmetry group gamma. The right-hand side will satisfy this kind of relationship. So this gives rise to invariant solutions for the state that we have U. So meaning that if I have a symmetry, like a rotational symmetry, I can take my nonlinear solution, rotate it, and find exactly and be still a solution of my system. However, in POD, because of the ergodicity and the exploration of all these possible symmetries, what ends up being the which does not correspond to the original nonlinear solution U. So somehow we would like to take into account the symmetry transformation in the POD analysis that I will show you now. And these two types of symmetries for gamma correspond to discrete symmetries like reflections, rotations, or shifts. Like, for example, here in the cylinder case, we can see the flow state reflected in two different instances in time, or we can have continuous symmetries. I showed you earlier rotation, but we can have also translation, which can give rise, for example, to traveling waves as well, if we have periodic directions. Here is a snapshot for the Kolmogorov case that I will show a bit later of the same state translated, I think is pi or pi over 2. And why invariances, they give a problem to the model reduction techniques like POD. First of all, is they bloat the latent space in the sense a symmetry transform states which equivalent are the same. They're encoded in different locations in phase space. So we don't need that because we will have much higher dimensionality in our system. But for most importantly for us, that we're trying to understand what are the underlying physics, excuse me, is the fact that we lose interpretability when we do POD analysis in the case of symmetry. Why? Because when we have a periodic direction, we can prove that the POD modes become Fourier modes. And when we have also symmetries, also the POD modes inherit the symmetries that the original system is equivariant under. And for that reason, inspired mainly from quantum systems, different solutions and statistical physics, different solutions have been proposed. For example, the method of slicing is one of them. So for tackling continuous symmetries or discrete symmetries by defining invariant polynomials. However, both are non-trivial methods and they require a priori data modification. And in some cases, actually, we don't even know, for example, what is the polynomial that will give us this invariance. So Simon actually came up with a really sophisticated way and simple in the same time to do that with the autoencoder architecture. So what we're doing is we start with a snapshot X, and we encode the optimal shift. We discover it. This is a shift S that we have to translate the whole state in a periodic direction, for example, in X, such that the reconstruction is optimal. And for the discrete symmetries, we replicate the same autoencoder architecture by creating a set of Siamese branches. So if we have a set of discrete symmetries, we produce by applying the same symmetry group to the snapshot to replicate all the possible states. And actually what we will do during the training is we will pick every time the one that is closest to that gives us the lowest reconstruction error. So then we just reconstruct back in the original space because we know which branch was selected and also what was the shift. And we back propagate the reconstruction such that we minimize the weights of the encoder decoder, and simultaneously we find the optimal shift such that the solutions become invariant in the continuous directions, but also invariant with respect to all the discrete solutions. So at the end of the day, the structures we will discover here, they're invariant under the pre-specified symmetry group of operations that we have defined at the beginning of the autoencoding. We will demonstrate that in the Kolmogorov flow, which is a canonical case for studying random events and very weakly turbulence. It has periodic boundaries in X and Y, and here you see a random event that the equilibrium solution is shifted after the random event happens in a completely different location by approximately pi. It has many different invariances due to discrete symmetries and also continuous symmetries. So the number of discrete symmetries are 16 symmetries because of the symmetry of the forcing, and the rotation symmetry. So during the encoding and the decoding, the architecture would tell us actually which of the states were explored every time the encoder was shifting the things such that solutions become invariant in this phase space now. So we can see here the PDF of these events, or just we're counting the events, and we can see actually that the data set is not ergodic, but this is not a problem for our method because every time we can condition based on the state of the system. And we can see only specific combinations of rotations and shift and reflect symmetries that have been explored by this specific system. On the right-hand side, I show the optimal shift that was discovered during a short period of time. And this is the shift that the autoencoder is applying every time a new snapshot is coming in, such that actually all the snapshots are aligned in the reduced space. And there is a direct relationship, and we can prove actually that this method that we're proposing is exactly equivalent to the method of slicing as well. The interesting part is when we compare directly the modes from the linear symmetry-aware PCA and the normal PCA. As I told you, if we apply normal PCA, the modes are just Fourier modes in the x direction, whereas actually they become physical modes in the SPCA framework, and specifically mode 1 corresponds to an equilibrium solution that can be found also based on operator-driven approaches, like dealing only with exact solutions of the Navier-Stokes. And the second and third modes actually are vortex modes that, again, they resemble some of the exact coherent structures that they can be found by Newton methods using the full nonlinear Navier-Stokes equations. How does the projection in terms of energy compare between POD and SPCA? Actually, with when we're using the symmetry-aware framework, the SPCA, and we project the reconstructed flow only using two symmetry-aware modes on the original PCA modes, we can see that we recover more or less approximately 100 PCA modes. So if we're actually taking into account the symmetries of the problem, we can see that we can drastically reduce the dimensionality of the system, and this results as well to a better interpretability of the results. If we include also nonlinearity in the autoencoders, but in that case we lose a bit the interpretability because we cannot plot modes, we can see that more or less we match exactly the energy of at least the 100 PCA modes with just two nonlinear modes. And this summarizes the second part of my talk about the symmetry-aware autoencoders that were inspired by the part one that I showed you. Simon has uploaded the code on GitHub for this method, and there is also an associated archive paper that I invite you to have a look if you're more interested. And the last part of my talk will be about some recent attempts on control, again inspired by the old results that we had. So the problem with the realistic application of flow control is actually the partial observability that we have. So we're trying not only to control a fully three-dimensional and turbulent system, but when we're trying to sense it, we have only surface information like pressure measurements, for example. And we will use already existing devices that we have implemented in a variety of vehicles, like active surfaces or spoilers, to try to move them in the specific case to remove or attenuate the symmetry breaking dynamics. So we did that in the new facilities at Imperial College. So we designed a canonical bluff body known as the Ahmed body. And we went back in the wind tunnel. We had two flaps on the sides, left and right, to kill here the bistability, the steady symmetry break that occurs in the presence of D2 symmetry. We used the original models. We had derived the stochastic models, and we have also the actuation taken into account there. And using standard actually control methods, we designed linear controllers to attenuate the bistability observed in these wakes. So we turn on the controller, and actually we can see that the center of pressure, Y here, it actually gets attenuated. And this gives approximately a 3% drag reduction of the total drag exerted on the Ahmed body. it was the first time that we realized actually that technique was very efficient. So we spent only a quarter of the energy to drive the actuators in order to gain this 3% drag reduction. And of course, 3% does not sound a lot, but still it would be at the margin of implementation in a realistic case. So to try to improve a bit more the efficiency, we tried different controllers, but actually no matter what we tried, we were always able to stabilize the low frequency dynamics at Struhar approximately at the limit of 0, as you can see from the black line, but we used always to attenuate high frequency dynamics. Okay, so there was always something missing in the model, some missing dynamics that we were not having, adaptability, something was changing, and we ended up causing things unwanted, and this would actually reduce the maximum drag reduction that we could potentially achieve. So nowadays we're following a counter shift in paradigm, so we're using reinforcement learning in a way to find controllers in a completely model-free way. Although reinforcement learning sounds something completely different, actually it's a sophisticated way to find feedback laws, feedback controllers by interacting with the system. In that case, in the reinforcement learning community, they call it environment. And there are many successful actually applications of that the last few years that they have shown promise for a variety of applications, including drag reduction for low Reynolds numbers, as it was demonstrated by Rabolt et al. So we're using an off-the-shelf algorithm. It's called the PPO, proximal policy optimization, that it mainly relies on two neural networks. These are actually defined the policy that we have to find and the critic that is there to optimize the policy to achieve an optimal reward or actually minimal drag in that case. So the actor that is seen here is a neural network that is actually a transfer function between the sensors and the actuators that is trained through the critic artificial neural network that we have here. So we interact continuously with the environment in order the critic to train something that can be used in a feedback loop that is receiving some information from the sensor and is driving the actuators. And I will demonstrate that either using two flaps for a laminar case here, or two synthetic jet actuators. And I will examine two cases, the one that we have full observability, so we have sensors everywhere in the wake, and in the other case, we have a more realistic scenario which corresponds to the partial observability, surface pressure measurements only on the base. If we train the policy with full observability, we can actually stabilize fully the wake. We can see that the drag is reducing approximately to the symmetric flow state, and actually the actuation is driving the wake in such a way that it becomes more or less symmetric. We can have 64 sensors to achieve full observability, but even with 8 sensors, we can actually gain similar results. However, when we have only a few sensors only on the base of the body, the drag reduction that we can achieve is much, much lower. And we have lost a lot of the performance that we had with the full observability. And there is a specific reason for that. This goes back to the theory of reinforcement learning, and specifically the underlying assumption here is that we need a full state information, it meaning that I need to measure all the states at the present in order to be able to make a prediction for the control action in the future. However, when I have only partial set of observations in the present, I cannot predict what is the optimal action that I have to take in the future to achieve stabilization. This can be bypassed easily using a Tachen's delay embedding theorem, which tells us that I can reconstruct the full state using partial observations by using a few delayed observations in my input signal. And nowadays in the control, in the machine learning community, this can be done in a more sophisticated way using recurrent neural networks like gated recurrent neural networks, LSTM, or even EcoState neural networks that optimally tune and find the dynamics of the recurrence or the past history that has to be implemented in the model, such that the state and the future actions are predicted in an optimal way. So on the left, we see actually by delay embedding, we can improve the drag reduction we can achieve. Not a lot, but we can see that by including 3 past observation, we can increase a bit the drag reduction. We can get much higher changes using gated recurrent neural networks for the actor and the critic architectures, and especially for the initial stages of the control that we think we can even optimally tune them a bit better. We can achieve more or less the results of the full observability case. This is the last slide that I will show you today, and this is one of my attempts to try to understand the reinforcement learning and not think that is actually a black box or a magic that is just giving you a controller. Actually, there is a nice correspondence with control theory, and once you include the recurrent neural networks or delayed observations, then the actor we're discovering, it has exactly the equivalent interpretation as a nonlinear digital filter that we would find with standard digital, with standard control techniques. So in that case, we can use all the control techniques to understand the performance of the controller. And the most typical one is the frequency response analysis. So I apply in my actor now, I see my actor as a transfer function, as an input-output system. I apply a harmonic signal as an input frequency, and I record the output frequency in all the frequencies. And I see actually that the main response is along the diagonal, which tells me that if I force at the frequency, I get the specific frequency at this specific frequency, which implies linearity. And if I plot the amplitude and phase associated with the maximum linear response, I can get actually a transfer function or a Bode plot describing the discovered now nonlinear controller, which is parameterized with a neural network and is known as an actor in this specific case. And specifically what we have discovered here, we can fit a second order typical linear system, and we can see actually that it matches very well the response of the nonlinear neural network. So these are some conclusions from the third and last part. But what I would like to say as a comment is that why we didn't do that for more complicated cases is because we couldn't afford it computationally. So I had to run 200 simulations to get these optimal controllers using DNS calculations here. For turbulent regimes, you might need even more simulations, and this is completely intractable, especially for the complex regimes we're looking at. So the whole idea in the future and what we're working now is to go in the wind tunnel and replace the environment instead with a numerical simulation with the actual experiment and obtain the interaction, so the response, the action and the response of the environment in real time in a fraction of a second, and do the training on real time in the wind tunnel. So with that slide, I would like to summarize. We mainly showed the persistence of the laminar structures, coherent structures at high Reynolds numbers. And we did that using the low Reynolds numbers and Navier-Stokes operator-based approach at the high Reynolds numbers, a data-driven symmetry-aware PCA type of analysis that also inspired us to develop the symmetry-aware method that I showed you. And finally, our recent attempts and understanding of recurrent reinforcement learning for controlling the bluff body wakes. With that, I would like to thank you for your attention and take any questions you may have.